Hello and welcome to our next lecture. In the last lecture we covered equations with either both ends being at the temperature 0, we call them zero boundary conditions, and we looked at the case when the flux at both ends is 0. So today we're going to mix things up. What if we have a boundary value problem for ut to satisfy an equation ut equals constant times uxx, and then we either have u of 0t being 0 and ux at lt being 0, or we might have ux of 0t being 0 and u at lt being 0. So we have when one of the ends is insulated and another end kept at temperature 0. And the initial condition is the same for both cases. Well, using the method of separation of variables, we again construct a solution as a summation of basis functions multiplied by some coefficients, where each one of those building blocks satisfies the original differential equation and the boundary conditions of. Just as before, we assume that each un of xt is a product of a function of purely x and function of purely t. For the purpose of clarity, let's consider the first case. When we have a 0 temperature at the end x equals 0 and 0 flux at the end x equals L. Then according to our separation of variables, we have for x of x and t of t we have that x double prime plus sigma times x should be 0, with x of 0 being 0 and x prime of L being 0. We also have an equation for t prime plus kappa sigma t should be 0. And there are no initial conditions on t imposed just yet. Just as before, we consider three different cases. Case 1, sigma being 0. That would mean that x double prime should be 0, which means that x is simply a linear function. Plugging in the boundary conditions, if x of 0 is 0, then alpha naught should be 0. Looking at the other end, we get that 0 should be x prime of L, which leads to alpha 1 should be 0, because the derivative of x is alpha 1. Therefore, x of x in this case is just a 0 function, and therefore no non-trivial solutions are obtained. Moving on to the next case, sigma being less than 0, meaning that we assume that sigma is minus lambda squared, we get the equation for x of x in the form x double prime minus lambda squared x should be 0, which leads to the solution having the form alpha 1 e to the lambda x plus alpha 2 times e to the minus lambda x. Plug in the conditions, we get that alpha 1 plus alpha 2 should be 0. What also should be 0 is the derivative at L, which means that alpha 1 times lambda times e to the lambda L minus alpha 2 times lambda times e to the minus lambda L should be 0. This is a linear system for unknown variables alpha 1 and alpha 2, and if we write it as a matrix system, we will find that the determinant of the matrix is non-zero, giving us that only one solution exists, and since it's a homogeneous system, the only solution possible is alpha 1 and alpha 2 both being 0. The last case, when sigma is greater than 0, we assume that sigma is some kind of a lambda squared constant. We get an equation x double prime plus lambda squared x equals 0, which gives us the solution that x of x is alpha 1 cosine of lambda x plus alpha 2 sine of lambda x. If we plug in the boundary conditions, we get that 0 should be x of 0, and that means that alpha 1 times 1 plus alpha 2 times 0 should be 0, which leads to alpha 1 being 0. Also, the derivative at x equals L should be 0. If I compute the derivative, I get minus alpha 1 lambda sine of lambda L plus alpha 2 lambda cosine of lambda L. Since alpha 1 was determined to be 0, we get that if cosine of lambda L is not equal to 0, that means then alpha 2 should be 0. And therefore, we get a 0 function or solution. So that's not a very interesting case. But if cosine of lambda L equals 0, then alpha 2 can be any constant. And lambda L being 0 means that it has to be an odd multiple of pi over 2. So it's either pi over 2 or 3 pi over 2 or 5 pi over 2. This is n equals 0. And the odd numbers are usually written as 2n plus 1. Which leads to x of x being some constant times sine of lambda, which is 2n plus 1 pi over 2l multiplied by x, and the constant sigma being 2n plus 1 times pi over 2l squared. Let me move it a little bit. Now, solving for t, we get that t prime plus kappa times 2n plus 1 pi over 2l squared times t should be 0, which means that the function t is some kind of constant times e to the power minus kappa times 2n plus 1 times pi over 2l squared multiplied by t, which again, without loss of generality, can be assumed that alpha is equal to 1, and therefore u sub n of xt will simply be e to the minus k times 2n plus 1 pi over 2l squared t times sine of 2n plus 1 pi x over 2l. And therefore, the original solution should be the summation. And this time n will go from 0 to infinity. Cn times this function. Easy to see that to satisfy the initial condition, I will have to plug in t equals 0, and then the exponential function would disappear, and I would have to compute the quarter period series for my function f of x. Through very similar computations, we will discover that in the case when the roles of the endpoints switched, when it is a zero flux at the zero end and zero temperature at the end L, we get, instead of a quarter period sine series, it will be the quarter period cosine series. Since I kind of ran out of space, I'm just going to write it here. In case of switched boundary conditions, change sine to cosine. Because quite frankly, we realize that we have to have a sine quarter period series only when we applied the boundary conditions for a function x. And had we had the x prime at 0 being 0, we would realize that it's the constant alpha 2 that has to be 0. And then when I use the other condition, when x of L is required to be 0, then again we would come to the conclusion that the cosine of lambda L has to be 0, and that means that lambda is again an odd multiple of pi over 2. So what I'm going to do now is I'm going to solve both of those problems, which are only different in the type of the boundary conditions they employ. So in the case of the first problem, I would have to write u of xt as a summation as n goes from 0 to infinity of Cn, and I would have to use the sine series. So I would have to have e to the minus kappa, then I would have to have an odd multiple of pi over 2, multiplied by the sine of odd multiple of pi over 2, times x, where Cn we found by integrating from 0 to L of the function f of x times sine of 2n plus 1 pi over 2l x dx, which in this case means 2 over 2 pi, the integral from 0 to 2 pi, f of x is x times 2 pi minus x times sine of 2n plus 1 times pi divided by 4 pi dx, x inside the sine. On the other end, for switched boundary conditions, my u of xt should be the cosine quarter period series. And the coefficients Cn are found similarly by taking 2 dividing by L, integrating from 0 to L of my function times cosine this time. We would expect the solutions to have the following behavior. The temperature at the end where it's supposed to be 0 will always be 0. And the temperature at another end will be tapering off to a function that's parallel to the x-axis, meaning the derivative will be 0. So let's switch to Mathematica and look at the solutions. For the first problem here, we have the function, we integrate with the sine series, we add up a series solution, and then we draw it. So this looks very much like the case we had before at the initial time, but now if I start changing t, we see what's different. The 0 temperature end at the left is kept at the 0 temperature. At another end, the temperature can be anything. It's that the flux is required to be 0, and we see the derivative at another end. And that's the property of the sine quarter period series. So we see that the heat leaves the rod through the 0 temperature end, but also what happens at another end is that the hot parts of the rod heat up the cool parts of the rod, and the temperature kind of evens out. But then we see that the temperature starts falling. If we switch the boundary conditions and we make another end insulated and the right end have a 0 temperature, then we will have to proceed with the cosine series. Using the cosine series, we get that the 0 temperature is now at the right end and the 0 flux is at the left end. And we see exactly symmetrical picture going on as we let t progress. The insulated end evens out the temperatures, but then the temperature and the heat slowly leaves the rod through the end that keeps the temperature at 0 level. So what about situations where the temperature at both ends is non-zero, or that the flux through both ends is a non-zero constant? Here I'd like to point out that in the case when we have a non-zero temperatures at both ends, we can have temperatures different. But when we have a non-zero flux, the flux should be the same for both ends. If the flux is not the same at both ends, then the method of separation of variables doesn't quite work. So this situation is slightly different from the case when we just straightforwardly use the separation of variables method. Here we can circumvent using this method by reducing the problem to something we already studied. We expand the function u of xt as a function w of xt plus a linear function in terms of x. If we differentiate the function with respect to t, then the linear function after w will disappear since it doesn't depend on t. And the second derivative with respect to x is just going to be w xx of xt, since the second derivative of linear terms is going to be 0 anyway. So its w function should satisfy the equation. If u satisfies the equation, then wt should be the same as kappa times wxx. Now, what should be the boundary conditions? In the first case, when we have non-zero temperatures at both ends, we get that u of 0t is t naught. It means that w at 0t plus alpha naught plus alpha 1 times 0 should be t naught. And u of lt, that should be tl, meaning that the w of lt plus alpha naught plus alpha 1 times l, that should be TL. We can cleverly change alpha naught and alpha 1 we get that W of 0t has to satisfy 0 end point conditions. For the initial value, presumably u of x0 equals f of x. That means that if I plug in 0 time into my u function, it should be equal to w of x0 plus alpha naught plus alpha 1 x. That means that w of x0 satisfies f of x minus alpha naught minus alpha 1 x. So in fact, we just rewrite the function u as a summation of a function w and a linear function, and then the function w has to satisfy 0 endpoint conditions with a slight change at the initial value. So we've reduced the problem to the problem we already studied. We would just say that alpha naught is t naught and alpha 1 should be t sub l minus t naught over l, and solve a new problem with boundary conditions w of 0t equals 0, which should also be equal to w of lt, and w of x 0 should be slightly modified f of x. We do know how to solve this problem. This is the zero temperature ends problem. So therefore, dealing with non-zero boundary conditions is really not that complicated. And here comes the question. Do I have to have f of x agree with the endpoint temperatures that I'm prescribing? And the answer is not really. We can think about it this way, that initially the rod was heated up so that the temperature distribution is f of x. And then at the time t equals 0, two ends, two devices were connected to the rod that will keep the temperatures now at t naught and tl. And so if the temperatures do not agree with the temperatures of the distribution f of x at the end x equals 0 and the end x equals l, then this will introduce a temporary jump, which will then disappear after a while as the ends of the rod heat up or cool down to the right temperature. Now suppose we have a prescribed flux. The trick is exactly the same. This time though, the non-zero flux doesn't prescribe what the constant A naught should be, because when I take the derivative with respect to x, the constant alpha naught will disappear. But the flux F naught would describe what the constant alpha 1 should be. It should be exactly F naught. So what we're going to do is we're going to say that u of xt is some function w of xt plus f naught times x. The constant alpha naught would be included in the solution w anyway, because when we have a zero flux problem, it does have a constant present in there from the cosine series. And the function w would satisfy the original equation with the boundary conditions the same as the insulated ends problem, when the flux through the both ends should be 0. And the initial condition should simply be f of x minus f naught x. And that's just the insulated ends problem that we already know how to solve. So here I have an example of a system that has prescribed temperatures at both ends. So I mean I have to figure out the linear term that I would have to add to the function w. Well, the constant alpha naught equals the temperature at the 0 end, and the constant alpha 2 equals 20 minus 10 over the length of the rod, which is 2 pi, times x. Now w would be a solution to the following boundary value problem. The boundary conditions for w will be 0. But the initial condition for w would be x times 2 pi minus x minus the function I just added to u. And then all I have to do is to use the same solution technique that I used in my previous lecture on the zero temperature ends problem. So here I made a function f of x, and I made a function v of x. Then I find the sine series expansion, because I'm solving the zero ends problem now, of the function f of x minus v of x. Then to create a solution, I take the function v of x and add the series expansion of f of x minus v of x. If I evaluate, this is what I get. The function f converges at both ends, but the problem in consideration prescribes the temperature 10 at the left end and the temperature 20 at the right end. And you can see how the sine series expansion tries to jump to 10 and 20 at both ends. As soon as I start increasing t, we can see that the ends quickly heat up, and then they pull the rest of the rod with them. And then as the time progresses, the temperature distribution converges to a straight line. Again, let's look at what happens during the first second. Very quickly, my ends heat up and the Gibbs phenomenon disappears. But it takes some time for the heat from the ends to reach the middle of the rod. But slowly but surely, it does happen. And then the temperature in the middle of the rod will start rising soon. As you can see here, the temperature at the ends of the function f of x does not agree with the temperature at the ends that I'm prescribing by boundary conditions. But this is not a big deal for the series expansion, and the behavior of the solution adheres very closely to physical principles. So this is how we solve the problems where we have mixed boundary conditions, or when we have boundary conditions that are non-zero constants, or we have a non-zero constant flux at both ends. I would recommend for you to play around with the constant flux problem, which means you would have to change these initial conditions to something of u sub x and u sub x at this end, but make sure you add the same constant right here. And just follow the outline that I prescribed on this page. So instead of subtracting v of x, that is alpha naught plus alpha 1 times x, you subtract a simpler function. And then you will be using the cosine series expansion, because that's what the solution is for the zero flux problem. This is where we're going to end today. Thank you for listening, and I'll see you in our next video.